This is the Prelab video for the acousto-optic modulator experiment for Physics 2213. In this experiment, we're going to use a device called an acousto-optic modulator to turn on and off a laser pulse. And so remember, our diode laser that we're going to use, our usual diode laser that we use, is a continuous wave laser, meaning it outputs a steady stream of photons. An acousto-optic modulator can do several things. But one thing which it can do is pick off some of that initial laser beam and put it into a secondary beam and turn that secondary beam on and off. And we'll be studying those sorts of properties in this experiment. The acousto-optic modulator works based on the principle of diffraction. There is a grating set up inside of an optical crystal, and that grating is generated by an acoustic wave. That acoustic wave is driven by an electrical signal, and that electrical signal comes from this device, which maybe you've seen around in the lab but don't know what it's for. This device is specifically an amplifier to drive the acousto-optic modulator. So this provides a signal which generates acoustic waves inside of a crystal, which creates a diffraction grating, which creates some diffraction, and a couple of other issues which you'll investigate. And so what we're going to need is to use the function generator to generate a signal. The signal generated by the function generator is not powerful enough. So we need to amplify it, and so that goes through this amplifier. And the amplifier then goes to the acousto-optic modulator, which is this device is sitting on the table. The crystal is housed in this device, and maybe we'll look at that a bit closer in a moment. So you have to carefully set up the electronics that won't be set up for you, and you'll have to understand what connections you're making and why. Remember, technically to note, the power switch for this device, there is a power switch, it's located on the back. This device, our function generator, remember that you can set everything up on the function generator, but until you push the output, you haven't turned it on. So remember, you have to push the output button, and then that turns green, and that means it's actually turned on. It's actually giving you a signal out. And of course, we'll use our oscilloscope to understand what signals that we're creating and sending out. Okay, so let's zoom in a little bit on the acousto-optic modulator itself. It's this device right here. There's a crystal inside of here. There's a nice figure in the lab manual that shows the cover taken off. But basically the laser comes in one side and goes out the other, and depending on whether a signal is coming into the acousto-optic modulator, you either have a diffraction grating on or you don't. And so when the diffraction grating's on, some of the laser power is split into higher order beams, first order, second order, third order diffraction beams. And well, that all works really nicely. Now the trick with acousto-optic modulators is there's a certain angle that they have to be turned at. So if this were perfectly perpendicular to the laser beam, nothing interesting would happen. This has to be turned at some angle in this sense, so that the diffraction grating is at an angle with respect, is not that the waves, the plane waves of the diffraction grating are not perpendicular to the direction of the laser beam. They have to be at some angle, the so-called Bragg angle, and that's something that you'll be investigating. So the fine adjustment is going to be for you to do this very careful rotation in this direction. And a nice way to do that is to have this thumb screw reasonably tight, not super tight, and then hold on to this part of the acousto-optic modulator, and you can do sort of a very careful, very smooth adjustment. And so you'll be playing around, you'll get a feel for that. There's a precise angle where you'll get the most power into the diffracted beams, and that's what you're going to do. In this experiment, we'll be using, of course, a photodiode to understand what's going on, or to investigate what's going on. But this photodiode is slightly different from the ones you've been using previously. I don't know if this one has been sitting on the optics table or not previously, but this one has a smaller photodetector on it, compared to our previous one that you've been using, which has a bigger active area, a bigger photodetector. And the difference is that the size of the photodetector affects the capacitance of the device, and the capacitance of the device affects how quickly you can changes of light on the photodetector result in electrical changes on the signal that you're reading. Right, so if you want to change something very quickly, you want to have a device with a very small capacitance so it can change very quickly. You can think of there being some RC time constant involved. And so you want to reduce the RC, so you want to reduce the C by having a smaller photodetector, and in the end we also want to reduce the R. Where does the R come from? It comes from, if we just plugged this device into the oscilloscope, we'd be dealing with the input impedance of the oscilloscope, which itself is something like 1 megaohm or 10 megaohms. Typically, measurement devices are reasonably high impedance, and that high impedance would affect, at some level, our time constant, or the speed at which we're able to register changes on the photodiode. And so we want to reduce that 1 megaohm, so that's what this is for. We have a T, and on one end of the T is a 50 ohm terminator. So basically we're replacing the high impedance input of the oscilloscope with a 50 ohm to ground impedance, and so that will allow the electrical signals to respond much more quickly to the changes in light. And so we'll be able to really investigate how quickly the light can turn on and off when we're using this acousto-optic modulator. Okay, so I think you have enough experience with the other components, the laser, the mirrors. Follow carefully the directions for the electrical setup and really try and understand why certain things are attached in certain places, right? Well, that will really help you understand what's happening in the lab. And again, this is perhaps the most careful optical alignment experiment that you're going to have to do. It's really adjusting the acousto-optic modulator angle precisely that will allow you to see the signal. But anyway, it's not impossibly hard, and you'll get a feel for it, and I'm sure you'll do fine. Good luck.